computing, and I'm happy to welcome Steven Sprague, the CEO of Rivetz.
Thank you, everybody. I hope everybody had a great lunch. So, you've talked a lot over the course of the last day and a half about blockchain and different applications, and we're here at the track also running with cybersecurity, especially around IoT. And what we do at Rivetz is combine many of those pieces together. And so we're going to talk about how we create provable instructions. Because one of the real challenges in all of this is that while we have all this great technology of the blockchain, it's important to understand that while the data stored on the chain never changes, it's not possible to prove that the data that we wrote to the chain was intended if all we have is the chain. So on the chain, I have a piece of data. It's signed. It's not changed since yesterday. We know in its sequence it is an immutable memory. What we don't know is that we have any evidence that the data that you wrote on the chain was what you intended. You might have borrowed your key. How do you know what he wrote on the data? You don't. And that's a really interesting aspect because we have no cybersecurity controls as part of the recording of the data on the chain. We don't bind it into the chain. We actually, if you really want to go check today, what you do is you go back and you get your Windows log files out, and you pull down the log files and you look to see whether your operating system was running in the right condition, you have the right keys, you look at your enterprise controls, maybe you look at some of the cameras to see who was actually in the room at the right time, and now you have all the information necessary. We're not supposed to be looking at Oracle databases to determine whether or not the data on a blockchain is correct or not. We need something more to have proof that a known device in a known condition with a known set of capabilities and a known user participated in executing of a transaction. And so, how do we bring the tools together to assert, by the way, this is an old problem. This is not a blockchain problem. This is called e-commerce. We've been having this problem since the beginning of time. How do I know when I send a transaction over the internet that it came from me, that somebody didn't steal my credit card? How do, the merchants that receive transactions, how do they know they're real? We're doing all this crazy stuff to try and prove that the instructions that we got, the payments we got, or the information we got came from the systems we intend. Part of the reason for this is because all of our cybersecurity controls have been built around a very simple model, which is one of a centralized castle. So we build castle walls, and inside the middle of the castle walls, we put the crown jewels. Right? And we protect the information by building a fence around it. And for years, we've spent $1 trillion of industry money on protecting the walls and looking and inspecting at all the content that goes through the walls, called network security. Now the problem is, as we move outside of the enterprise and we go to the cloud, we put the crown jewels in the cloud. And that's okay. The problem is, it's really hard to go put a fence around the whole cloud. Now, some people are trying to do this. You could argue that this is, interesting models where all of a sudden we run all of our traffic back through the enterprise network to the cloud so we can inspect the traffic and make sure the right transactions are happening in the right ways. So then along comes the blockchain. The way to think of the blockchain is, we put the crown jewels everywhere. Now, so this is cool because it creates this decentralized game theory-based model of computation so we can assure that we don't have double spend, that we have the correct transactions in the right space. This is a fantastic model. The problem is, I can't tell when I send an instruction to a specific node. There's no network security that's going to watch all of the nodes. You have some projects like Hyperledger that are trying to do this. Put a fence around every node, which is a perfectly fine idea. It's a way to take our $1 trillion investment in cybersecurity, run the blockchain inside the fence, and then I can look and say, hey, we got a lot of traffic coming from Russia today that's trying to affect our chain. We shouldn't have any traffic from Russia. So something must be going on. Where if we look at the previous picture, how would you know that the traffic's coming from somewhere else? You don't. And so we've just eliminated, by adding blockchain to the project, all the cybersecurity controls that we've had in the past. So it's a really interesting challenge. It is an incredibly valuable new tool, but we have to start bringing back some of the controls that we need in order to assure the data we write to a chain is the data that we intend. I come from an industry where we spent 20 years deploying trusted execution into devices. So my background is in the trusted computing space. It was part of helping the early stages of how do we put hardware security into every device? How do we put, whether it's trusted platform modules or TE environments? They're now part of Intel Core processors, have something called SGX as part of every processor. I think you've heard some about that from the Microsoft folks, and certainly from Intel. Inside the ARM processor on everybody's cell phone is a trusted execution environment in which we can hide and process secrets. And we do that independent of the operating system. So it's a measured execution environment that creates a space that we can assert if the code that's measured, which is done with digital signatures, is in the state we expect it to be, then we have a certain level of protection. Nothing's absolute. This is not like all of a sudden I've got Fort Knox on my phone, but I might have a really good $1 million vault on my phone. I wouldn't put $1 billion in it, but I'd probably be very comfortable carrying around $100,000 in a trusted execution environment on a handset. You know, it's just like when you buy a safe at home and you put it in the closet. Some people go to Staples, they buy a safe, they go home, they put it in the closet. Turns out that's not very safe. You can just pick the thing up and take it. What you really should do is put a bolt through the back of the safe into the wall in the closet, which requires at least a crowbar to remove the safe from the wall, and definitely slows down the drive-by theft of all your valuables, which, by the way, you put in a convenient box in the closet. Take the box. It's really not a problem. Or in the case of my mother's old house, I think the safe in the basement is like 3 tons. We're contemplating trying to figure out how to move it. I think we'll just sell it with the house. It's like, that's a good safe, right? It's too heavy to move. So these are standards-based technologies that allow us to form and protect instructions, because authentication is not enough. You think about authentication, we're not logging into the blockchain. Nobody logs into the blockchain. You never, ever, ever log into the blockchain. You do what an Internet of Things transaction should be. You send the blockchain an instruction. You say, move this much from this account to that account, leave these residuals behind. It's a signed instruction. It's like a nuclear launch code, like a movie version of nuclear launch codes. You have an encrypted football, you form inside an instruction, you send it off to a silo, and they should do nothing with the instruction unless all the signatures check. All the signatures check, they should push the buttons and do whatever the instructions say. It's a very similar concept. IoT is very much along the same lines. So trusted execution today exists in millions of devices. One of our partners that ships a TEEOS, which allows us to provision these trusted execution environments over the air, just shipped their 1 billionth copy of software last May. So there are 1 billion Android phones in the last 4 years. So that means there's 500 million of them that are still available. The other half of them are in a drawer somewhere, or the kids lost them in the mud, or broke the screens, or cell phones have a couple-year life. So there's probably about 500 million active Android devices globally today that have a trusted execution capability within the device that we can provision and take advantage of. There are about 500 million PCs also. So don't forget the PCs when we think about mobile, just the fact that it's this big. It's actually about the processor architecture and the security capabilities of the device. Intel's now shipping trusted execution as part of every one of their processors. So the ability to hide and process secrets is really core within that. Also, these technologies support things like trusted user interface. So my Samsung phone, I can draw an image on the screen that's drawn not by the operating system. It's actually drawn by the trusted execution environment. So I can put a display on the screen, can't be read, altered, or compromised by the operating system. That's cool, because if we want someone to do a transaction, we'd like to tell them what is the transaction we're going to do. And if the screen is going to lie to you, that would be a challenge. People are mostly surprised when I tell them that Intel shipped 950 million laptops. That's 950 million laptops with trusted display. Nobody ever turned it on. It would secure your e-commerce for all your shopping online. Nobody turned it on. We don't believe that our devices are an important thing. We're here at an IoT conference, and we still aren't really quite sure that a user logs into a device, the device should log you into all the services to which you belong. Let's get rid of passwords. Humans don't need passwords anymore. So I find this to be a useful process. And forgive me for those people who know this, but I was in the industry for almost a decade before somebody really took me through this and I understood. When you do a credit card transaction, like if you go to Paris and they bring a little Ingenico terminal to your table when you buy an espresso for €2, and you put your chip card into the machine, there are 3 core hardware components of security. The first one is trusted display. On that little screen, whether you're at TJ Maxx or you're, got that portable terminal in front of you, is the transaction you are consenting to. The second thing is some form of user consent, a PIN number, a biometric, so that the human's saying, yep, that's what I want to do. I want to spend $49.85 at Target. And then the third piece is that there's a chip inside a card that holds a private key. We're all very focused on the private keys, but we always forget about the first 2 pieces. So the private key then signs the instruction. Now all of that is really great. How do we know it's working? So it turns out there's a 4th layer, which is attestation, which is how we verify that the other 3 pieces are working correctly. And so one of the really interesting pieces is to build the attestation layer across the blockchain that allows us to insert some quality bits into the chain in a manner that has really good privacy controls, yet really good support for cybersecurity controls on peer-to-peer transactions. So the role of attestation is this understanding of what are the measured components and were the measured components in the condition I expected them to be. There's no absolute truth here. In most cases, it's just, has it changed from yesterday? If I didn't update my system and my underlying system changed, then something's going on. Should I be doing $1 million transactions on a system that is unknown compute? Well, that's what we do every day. Today we have known users, unknown computers. The entire system, all our SCADA systems, all of our IoT systems, all of our automotive systems, they're all running on unknown compute. We don't characterize the underlying compute and we don't record it. Now, attestation is an interesting technology because what I really would like to know is take a snapshot of a system, which is a signature, and store it someplace where it won't change. Blockchain would be perfect for that. So what we do is we write an attestation record into the blockchain so we can come back and then test to see whether or not that transaction has changed. So Rivetz as a company has actually just begun building a token model. We started actually a year ago October actually was our first demonstration of it, where we incorporate this attestation model as part of not only a financial transaction, but also an operational transaction embedded directly into the chains. It'll come in a variety of different forms. So it's a new, interesting mechanism. We're very excited about the utility aspects of tokens in the market. This is a true definition of a utility token for a cybersecurity control. It operates the cybersecurity control. And so what we've done is a simple system where a device can be verified as it does transactions, but one of the cool things we learned is that not only can we test the internal integrity of the device, but we can also ask the device to ask external systems to incorporate additional data. You can think of it, if you know what smart contracts are, like having an oracle. In this case, the device with the chip in it is requesting to a cybersecurity control marketplace data about that device. Like, hey, what state are you in? If you're in the state of Nevada, we can gamble. So go check and see whether I'm in the state of Nevada, because I'm not allowed to spend this gambling money unless I'm in the state of Nevada. Right? And so now we can do that kind of control by having the trust agent in the device make that request and incorporate it into the actual signing of the transaction to allow it to execute. And the transaction won't go forward if the reference integrity measurement doesn't match the real time. So if you're not in compliance with the real-time measurement according to the owner of the platform, so the owner is in charge of this process, the owner decides, do I meet those controls? And now I can assert because the evidence has been left on the chain. In essence, I have a signature that's bound into my transaction that says, this device was in this provable condition when the transaction was executed. And so this becomes a really interesting mechanism to approach how do we have control, but we can automate the process with machines. So like if machines want to automatically spend money, we always talk about machines are going to automatically spend money. How do you prevent machines from spending the money when any good-looking bot comes by and says, hey, give me some money, right? It's actually a really interesting challenge to how do I put a policy fence around it. So this is very different money than like Bitcoin. We want anonymous money in Bitcoin. We don't want it tracked. No, this is my money for my robot. I want to know exactly what my robot's spending its money on. It's not allowed to spend its money on things it's not allowed to spend money on. I don't want bots asking for money. You've got to have control over this. This is the other end of the spectrum, because if we want machines to automatically solicit services, we're going to have to control and permission that process. Otherwise, it'll get out of control very quickly. So a token mechanism is a really interesting mechanism. It's going to be interesting to insert this alongside and in partnership, whether it becomes what we've been referring to as a machine multisig, where a transaction that's supported on anybody's token in any scheme, as long as it supports a multisig property, could ask the machine about its health and integrity, or the transaction won't be allowed to go forward. So it can become one of the keys in a multisig transaction. It can become directly embedded in the chain. What we did last October, we modified one of Blockstream's side chains. We added a couple of opcodes to it so we could support actually embedded in the pay-to-script process a test of does real-time equal reference for cybersecurity control, and bound it into the transaction on the chain. So you can go all the way from a completely embedded to a completely external solution in the marketplace. And so this is about high assurance messages. When we think about Internet of Things in any context, I want to make sure that a known device in a known condition produced that instruction. Whether it's to unlock the car, whether it's to start the pump, whether it's the speed of the insulin pump that's pumping it into the patient. How do I know that when the instruction was sent to that other thing, that the instruction was intended, that there were cybersecurity controls that were present, and that this will function on a decentralized and peer-to-peer mechanism? This is a way that we move away from a network security context and instead to a decentralized security context where the security is bound into the device transactions as they're deployed across the network. Because that's the point where the owner still has control. They control their devices. And so they can decide what quality is brought to those cybersecurity controls. And I think replacing some of the risk factor conversations with a quality conversation really helps this argument and discussion going forward as to how do we improve the quality of the data that's stored on the chain and have some ability to assert that this data was intended. So if you actually ask me to prove it, I can now do a transaction on the blockchain where the only evidence I have is the chain. I can say, yes, a device in a condition that I expected with the controls for those keys that I expected produced that transaction, which is very different than just the key did. Because if I lose control of the key, I have no way of knowing whether it's me doing transactions or somebody else with my key. And I can't assert that it was only me. And so it's a really interesting challenge in blockchain to bring, on this decentralized basis, a shift away from a network security model to a decentralized security model, and that's what we're trying to bring to the party. So it's a fun conversation. We'd love to engage in any further conversation with anybody. This is going to require an army of people to ultimately deploy and scale across the networks. It belongs as part of every project. If you're storing the Ferrari keys, don't put the Ferrari keys in the Android phone with the same security that Snapchat has, which is the operating system. You can't hold the keys safe. You can't process the instructions to start the Ferrari. You'll lose all the keys. It would be a great dark web hack. You just like snap the VIN number, and then you download the key for the Ferrari that's parked on the street, and you just like go bleep, and then get in and drive off. It'd be awesome. We just need one app to steal all the Ferrari keys. It won't be that hard. So that's our approach to the market. I think we have a couple minutes if anybody has any questions. I'm so happy to finish there with a couple minutes for questions if you have any. Yes?
The encryption key that's in the device, is there a copy of it stored anywhere else
them, there can be. The way these systems are built, you generate a key pair within the device if you choose to have that private key never exported and mark it never exportable. Unless you compromise the hardware, it'll never be exported. On the other hand, I can write software that says, hey, make a damn copy of the thing because I'm going to lose my phone in an hour, right? And so I would like to have it stored somewhere else because, like, maybe on one of my other devices. I actually think that one of the interesting aspects here is don't think of your singular device as your identity, think of your collection of devices as your identity. Because you're going to lose your phone. Now, the beauty of losing a phone is, if you lose your phone, what happens? You notice. Like, if you're 14, have you ever watched a 14-year-old lose a phone in your house? Like, you can't do anything else. The whole house comes to a stop. Like, we cannot go out, Dad. We have to find the phone. Right? Why? Nobody's going to come. No, we have to have the phone. You can't remove it from the end of their fingers. Right? That's what you want. We want human-trained, continuous monitoring of a cybersecurity control. We want it ingrained in your DNA, and we want your mother to have taught you it. I don't want to pay some training guy in class. Don't lose your phone. No, your mother taught you that if you lose something valuable, panic. And so when you lose your phone, you panic. Like you have an actual DNA response. It's like, oh my God, I lost my phone. Excuse me, I got to stop talking about it. I left my phone in the other room, and I got to go find it.
So follow up with that, and where I'm going with this for any of the legal people in the room. The reason why I asked where it's stored, if I were to subpoena the company and say, give me the encryption of where or who has it, is that capability?
I think the legal proof is delightfully entertaining here, and the technology is legally agnostic. So can I get to the point where you can't subpoena the key because there's no way to recover it? Yes. On the other hand, can I create a system where you can subpoena the key because it is recoverable? Both are possible. Different systems may benefit from different ends of that spectrum. So can I build encryption? I can show it to you on my phone today. It's nation-state proof that will allow you and I to have messages. Cool. So let's go start a terrorist bombing campaign because now we can chat about where we're going to do it, when we're going to do it, how we're going to do it, how big the bomb is going to be, and nobody can watch. Is society ready for that? Not really. They really actually, if they found out we were all chatting on that app, we're going to be out, the brand will be out being run underground. So it's an interesting challenge, this model, as we move forward, because what is going to happen with IoT is that we're moving to device identity architecture with messaging as its primary protocol. Those messages are going to be encrypted. So nobody's going to be able to listen anymore. We're within a decade that you can't listen anymore. And it's going to take us a while as a social construct to get used to the idea you can't listen anymore. You can do lots of other things, but you won't be able to listen. Anyway, I think my time is up, so if you have questions afterwards, I'm here, and thank you for your time.